Welcome and settle in. Tonight, we begin in the year 1939, when two young theorists published a paper about the death of a star and, in doing so, helped open one of the strangest chapters in the history of modern science. Robert Oppenheimer and Hartland Snyder described a collapse so complete that once it began, nothing in the familiar architecture of matter could stop it. To a distant observer, the star would seem to slow, redden, and fade at the edge of its own gravity. To the matter falling inward, the journey would continue toward a region from which no message could ever return. It was a breathtaking idea, and at the time, it was far too strange for most people to grasp its full meaning. If you place yourself inside that intellectual world, the atmosphere feels both elegant and uncertain. Einstein's general theory of relativity was still new enough to be admired, argued over, and only partly trusted in its most extreme implications. The equations suggested that space and time were not passive stages on which nature performed, but active structures that could bend, deepen, and close around mass itself. Yet even many brilliant physicists hesitated before these consequences. The mathematics seemed to point toward a kind of darkness that violated ordinary intuition, a place where light could disappear and where the mind, trained by daily experience, could no longer guide itself safely. What makes this story so compelling is that black holes were never discovered in a single instant, and never by a single scientist. They emerged slowly through fragments of insight, through resistance, through arguments that stretched across generations. A forgotten clergyman imagined invisible stars in the 18th century. A gravely ill mathematician found the first exact solution to Einstein's equations from the front lines of war. A young astrophysicist was challenged for following the logic of stellar death too far. Later came theorists who gave this impossible object a clearer shape, and observers who learned how to detect what could not be seen. So tonight, we are not only entering the history of black holes, we are entering the history of an idea that took centuries to become believable. How do scientists discover something that emits no light, offers no surface, and resists every ordinary image the mind tries to form? And what does it mean that one of the darkest objects in the universe became one of the clearest victories of human thought? Step outside for a moment into an 18th century night, and let your eyes adjust slowly. The last candle inside the house has been covered. The final warmth of the hearth is beginning to sink into ash. Beyond the glass, the world is nearly unlit except for the sky itself, and the sky is immense. Without electric glare to soften it, the darkness feels complete, not empty but full, as though the air above the fields were holding its breath. Stars appear in their thousands, sharp and remote, set inside a blackness so deep that the mind cannot measure it. And as often happens under a sky like this, sight gives way to speculation. The visible things do not feel sufficient. The bright points are there, of course, but so is everything between them. The eye catches the lights. The imagination begins to ask about the dark. There is a particular mood that old astronomy could produce, especially before modern instruments turned the heavens into charts, numbers, and exposure times. It was a discipline of looking, but also a discipline of doubt. The night sky seemed orderly, yet the order itself suggested hidden structures. Bodies moved in ways that could be predicted. Comets returned. Planets wandered and were tracked. Moons circled worlds too distant to touch, again and again. The heavens showed that reality was not limited to what the unaided eye could immediately understand. A point of light might be a world. A wandering star might be a planet. A slight irregularity in motion might betray the presence of something unseen. Long before the modern language of invisible matter or collapsed stars existed, astronomy was already training the human mind to trust inference over appearance. That habit of mind matters here, because the first real ancestor of the black hole did not emerge from a photograph, a radio signal, or a 20th century observatory. It emerged from thought carried patiently to its limit. It arose in a world shaped by Isaac Newton's laws, where gravity had become something astonishingly powerful in the history of ideas, no longer a mystery in the old philosophical sense. It had become a principle that seemed to govern both apples and planets, tides and moons, falling bodies and celestial motion. Gravity tied together the local and the cosmic with a single mathematical thread. Once that thread existed, thinkers were almost compelled to pull on it and see how far it ran. By the late 18th century, natural philosophers lived in a universe newly disciplined by law. The heavens were no longer merely symbolic or theological. They had become mechanical in the deepest sense. Though mechanical did not mean dull, it meant that nature could be followed through reasoning. If one knew enough about mass, distance, and motion, one might extract truths from the sky that had never been witnessed directly. This was one of the great transformations of scientific culture. The universe had become legible enough that unseen things could be proposed seriously, not as fantasy but as consequences. The old human experience of staring into darkness had acquired a new companion: calculation. Among those willing to think this way was John Michell, an English clergyman and natural philosopher whose name does not echo through popular science in the way Newton's or Einstein's does, but whose imagination reached into remarkably distant territory. Michell belonged to that older intellectual world in which a learned man might move between geology, astronomy, magnetism, and theology without feeling that he had crossed into separate kingdoms. He was curious, mathematically literate, and unusually comfortable with indirect reasoning. He did not need a thing to present itself plainly before asking whether nature's laws required it to exist. In that sense, he possessed a quality that appears again and again in the early history of major discoveries: the willingness to take a theory seriously, even when it leads somewhere that no ordinary experience prepares us to go. One of the important ideas available to Michell was the notion of escape velocity. In modern life, the term belongs easily to rockets and spaceflight, but its logic was already present in Newtonian mechanics. To leave the pull of a body, an object must move fast enough. The stronger the body's gravity, the greater that required speed becomes. It is a simple idea, and like many simple ideas in physics, it becomes more startling the longer you follow it. If mass increases and size decreases, gravitational pull grows stronger. If that process continues far enough, the speed required for escape rises higher and higher. A question begins to take shape almost against one's will. Could it rise so high that even light would fail? Today, that question feels almost prearranged, because we know where the story will eventually lead. But in Michell's day, it was an act of unusual daring. In 1783, writing to Henry Cavendish, Michell proposed that a star might exist with such strong gravity that light itself could not escape from it. It would not shine in the ordinary sense, not because it lacked reality, but because its own gravity would trap its light before that light could reach distant observers. The phrase black hole did not exist. The language of curved space-time lay far in the future. Yet the conceptual shock was already there. Michel had imagined an object that was real, massive, and in principle invisible. The elegance of his thought lies not only in the idea itself, but in the way he tried to make it scientifically meaningful. Michel did not leave the dark star as a mere curiosity. He suggested that such an object might still be detected indirectly through its gravitational influence on a visible companion. If a luminous star appeared to orbit around something unseen, then the unseen body might reveal itself by motion alone. This is one of those moments in the history of science that feels quietly uncanny in retrospect. Not because Michel had discovered the modern black hole, which he had not, but because he had already grasped a method that would later become central to black hole astronomy. The hidden object may be invisible, yet the world around it cannot help but testify to its presence. There is something almost literary about the timing of that insight. It came before astrophysics, before relativity, before any workable means of observing such extreme objects, and before the broader scientific culture possessed a stable framework for making sense of them. The idea was disciplined, but premature. It was lawful, but homeless. Michel had reached a shoreline that physics itself would not truly inhabit for more than a century. In historical terms, this is one of the strangest things ideas can do. They can arrive too early to survive in full, like seeds dropped into ground that is not yet ready to hold them. Pierre-Simon Laplace, working in a similarly Newtonian intellectual universe, later entertained a related possibility. In his own treatment, sufficiently massive bodies could prevent light from escaping. This parallel matters because it shows that Michel's reasoning was not an isolated eccentricity. The laws of the time were beginning to point multiple thinkers toward the same frontier. Once gravity had been mathematized with enough power, it became possible to imagine extreme bodies even when no one had seen them. And yet this convergence did not create a new field. It did not launch a sustained search. The thought existed, was noted, and then receded again. Part of the reason lies in the scientific world around it. 18th century astronomy was rich in observation, but not equipped to pursue such a subtle quarry. A body that emitted no visible light would not easily enter the practical routines of the observatory. One might speculate about its influence, but the precision needed to identify it reliably was still far beyond what most astronomical work could support. There is a quiet lesson in that. Science does not move forward on logic alone. It requires a culture of attention. It requires tools, priorities, language, and a community prepared to treat a possibility as worth sustained labor. Michel's dark star possessed the first of these, but not enough of the others. It also belonged to a universe that was still, in an important sense, too comfortable. Newton's cosmos was magnificent, but stable. It allowed extremes. Yet it did not naturally encourage physicists to imagine the internal death of stars, the collapse of matter under its own gravity, or any geometry so severe that time and light themselves would behave in radically unfamiliar ways. The dark star could be imagined there, but only as an extreme consequence of known mechanics. It did not yet carry the sense of a deep rupture in our understanding of reality. For that, the foundations themselves would have to shift. Still, the idea lingers. And it lingers not because it was already the full truth, but because it contained something psychologically essential to the later story. It taught science, very early, that darkness might be active rather than passive. The unseen was not merely what had escaped notice. It could be what law itself required. even when observation remains silent. That is a profound change in intellectual posture. Instead of asking only what shines, one begins to ask what governs. Instead of trusting presence, one learns to trust consequence. This is why it would be too simple to say that Michel discovered black holes in the modern sense. He did not. His world had no general relativity, no space-time curvature, no event horizon, no modern understanding of light as a limiting structure woven into the fabric of the universe. The dark star was a Newtonian object, born from escape velocity rather than geometry. But it would be equally misleading to dismiss the idea as merely quaint or accidental. What Michel found was a genuine conceptual threshold. He had walked far enough into the logic of gravity to see that invisibility itself could have a lawful cause. That threshold deserves to be felt, not just summarized, because it tells us something about how large scientific ideas often begin. They do not always appear as complete systems. Sometimes they enter history in fragments, wearing the wrong vocabulary, attached to the wrong theory, or isolated from the methods that might one day confirm them. They may look less like discoveries than like strange pressures within thought. A disciplined mind reaches the edge of what a theory can say and glimpses something that does not yet belong to its time. The idea is not fully usable. It cannot yet anchor a research program. But it leaves a mark. It widens the possible. As the 19th century unfolded, that widened possibility did not become one of science's central obsessions. Other revolutions crowded in. Heat became statistical. Electricity and magnetism were unified. Geology deepened the age of Earth. Evolution transformed the history of life. Chemists and physicists revised matter itself. Astronomy grew more precise, more instrument-driven, more occupied with stellar classification, spectra, and celestial mechanics. Under those conditions, Michel's invisible star had little room to mature. It remained one of those nearly forgotten ideas that later historians love because it seems, in retrospect, to gesture toward a future no one could yet see. Yet even as it faded from direct attention, the deeper habit behind it endured. The sky continued to teach scientists that what mattered most was not always what announced itself plainly. Uranus would later be found to move in ways that suggested an unseen influence, and that influence would help lead to Neptune. Binary stars would become crucial laboratories of inference. Spectra would reveal chemical signatures at impossible distances. In many ways, modern astronomy grew by becoming comfortable with hidden causes. The visible universe was only the beginning of the evidentiary field. That way of thinking would eventually become indispensable to the black hole story, because the object at its center would resist every ordinary mode of direct encounter. So when we look back at the dark star, we are not looking at a failed black hole theory. We are looking at an early rehearsal for a different kind of scientific courage. Michel and Laplace were willing to believe that the consequences of gravity might lead beyond the visible sky. They allowed the laws they trusted to carry them somewhere. Intuition alone would never have gone. That movement, from observation to abstraction, from the seen to the inferred, is one of the most important intellectual motions in the entire history of science. And here it appears in a particularly haunting form, because the destination is not some new shining world or hidden planet, but a star defined by the fact that its light never arrives. There is another reason this beginning matters. It reminds us that the history of black holes is not simply the history of technical progress. It is also the history of a slowly changing imagination. Human beings had long associated darkness with absence, ignorance, or the limit of sight. But the dark star introduced a more unsettling thought. Darkness might be presence in its most concentrated form. It might not mark a place where nothing is. It might mark a place where too much is happening for light to escape. That reversal is subtle, but it carries enormous force. It changes the emotional meaning of the night sky. Imagine, then, that same 18th century observer standing beneath the stars, unaware of relativity, unaware of stellar evolution, unaware of the cosmic violence later physics would uncover, and yet already living close to one of the deepest questions in our story. If some of the most powerful bodies in the universe do not shine, how could they ever be known? What kind of science is required to discover something that withholds its own light? Those questions would not be answered in Michel's lifetime, or in Laplace's. They would wait while physics itself transformed. But the first movement had already begun, and perhaps that is the right way to leave this opening threshold, not with a conclusion, because none has yet been earned, but with a sense of pressure gathering beneath the old framework. Newton's universe had allowed a startling possibility to appear, then left it unresolved. The dark star stood at the far edge of 18th century thought, like a silhouette half formed in mist. To bring it fully into view, science would need a new theory of gravity, a new understanding of light, and a new willingness to accept that reality may be stranger than the inherited geometry of common sense. The sky is still dark as we move forward, but it is no longer the same darkness. Somewhere ahead, space itself is preparing to bend. Time is preparing to loosen from its old certainty. And when that happens, the old invisible star will return. Not as a speculative curiosity at the edge of Newtonian mechanics, but as something deeper, harsher, and far more difficult to ignore. The old dark star had not disappeared because anyone had disproven it. It had simply drifted beyond the center of attention, left behind in a scientific world crowded with other revolutions, other urgencies, other forms of intellectual excitement. During the 19th century, physics and astronomy became richer, sharper, more ambitious. Heat was reimagined. Electricity and magnetism were drawn together. Spectroscopy began to tell astronomers what stars were made of, and celestial bodies slowly lost some of their ancient remoteness, becoming physical things rather than distant ornaments. Yet beneath all that progress, gravity still held on to a certain mystery. Newton's law worked with extraordinary power, but it described attraction across space without ever quite making that attraction feel fully explained. If you place yourself in the first years of the 20th century, the atmosphere feels brilliant, but strained. The visible universe had become more knowable than ever before, and still the foundations of physics were beginning to tremble. Light sat at the center of that unease. The more closely physicists studied it, the less comfortably it fit inside the older picture of space, motion, and time. Then, in 1905, Albert Einstein published the work that would later be called special relativity, and the familiar stage on which physics had been performed began to shift. Space was no longer passive. Time was no longer universal, and the speed of light emerged not merely as a property of illumination, but as one of the fixed features of reality itself. That change did not yet produce black holes. It did something deeper than that. It changed the world in which any future black hole would have to exist. Michel's dark star had belonged to a Newtonian universe, where gravity acted as a force and light was treated within that older mechanical frame. Einstein's new world began to dissolve that arrangement. If light had a special status in nature, And if space and time were bound together in ways that changed with motion, then gravity could no longer remain what it had once been. Something more radical was beginning to take shape. That deeper account arrived in 1915, when Einstein completed the general theory of relativity. The change is so famous now that it can sound almost too polished in retelling, as though one elegant picture had simply replaced another. Historically, it was far more unsettling. Gravity was no longer to be understood merely as a pull between bodies. Matter and energy shaped space-time, and space-time, in turn, shaped the motion of matter and light. Objects followed the curves of a geometry that mass itself had helped create. Time passed differently in stronger gravitational fields. Light bent when it moved through that curvature. A theory that had begun by revising motion now revised the architecture of reality itself. Even today, there is something psychologically difficult about that step. Curved space-time is not the kind of idea ordinary intuition welcomes easily. It asks the mind to give up habits formed in everyday life, and to accept that what seems like force may, in a deeper account, be structure. For physicists living through those years, the elegance of the mathematics did not automatically erase the strangeness of the interpretation. General relativity was admired, certainly, but it was also abstract, demanding, and unlike the language most scientists had been trained to trust, it still had to be solved, tested, and slowly made inhabitable as a physical way of seeing. Then, almost immediately, the new theory produced a result that made it stranger still. In 1916, Carl Schwarzschild found the first exact solution to Einstein's field equations for the space-time outside a spherical mass. At a distance, that phrase can sound merely technical. In truth, it was one of the decisive achievements in early relativity. Einstein himself had often worked with approximations in order to extract predictions from his theory. Schwarzschild showed that, at least for a simple but fundamental case, the equations could be solved in full. And he did this while serving on the Eastern Front during the First World War, under conditions that make the achievement feel almost unreal in retrospect. Amid mud, illness, artillery, and military duty, a mathematician was tracing the shape of gravity with extraordinary clarity. There is a particular sadness around Schwarzschild's place in this story. He enters it briefly, almost with the quality of an apparition, and leaves behind a result that later generations would return to again and again. He was already ill, and he died in 1916, the same year his solution appeared. Yet the geometry he uncovered would remain at the center of gravitational physics long after his own life had ended. That contrast gives his contribution a haunting kind of permanence. The man disappeared quickly. The structure did not. The Schwarzschild solution described the space-time surrounding a non-rotating, spherically symmetric mass. Hidden within it was a characteristic distance, later called the Schwarzschild radius, for an object with the mass of the sun. That radius would be only a few kilometers if all the mass were compressed inside it. To a modern listener, that almost immediately sounds like the threshold of a black hole. But that recognition belongs to hindsight. Early readers of the solution did not yet possess the settled language that would make such an interpretation feel obvious. What they saw first was something disturbing in the equations themselves. At a certain radius, the mathematical form appeared to become singular, and then, deeper in, another singularity appeared at the center. This is where the story becomes subtler than the clean version often told afterward. Mathematics does not always reveal its physical meaning in a single instant. Sometimes it reaches farther than the shared intuition of the people reading it, and its symbols must wait for later generations to understand what they truly imply. Schwarzschild had found a solution of remarkable depth, but the status of its strange features was not yet clear. Was that outer singularity something real in nature, or merely a problem with the coordinate system used to describe the space-time? Was the theory showing a genuine boundary in the world, or was it exposing a weakness in the way physicists had first written the equations down? Those questions did not yield quick, confident answers. In later retellings, the path from Schwarzschild's work to the black hole can seem almost inevitable, as though the object had been sitting there in the mathematics, waiting only for someone to name it. The lived history was much less straightforward. Early relativists were moving through a region of conceptual fog. The theory itself was young. Its most extreme implications felt difficult to naturalize. The vocabulary that later generations would rely on was not yet stable. What we now call an event horizon did not yet exist as a settled idea. The geometry had gone somewhere extraordinary, and the people reading it had not yet learned how to follow it all the way there. To say that the equations already contained a black hole is, for this period, both true and misleading. It is true in the limited sense that the mathematical structure was there. It is misleading because the object had not yet become a stable inhabitant of the scientific imagination. The concept was missing its mature interpretation. The causal picture was missing. The distinction between a true physical singularity and an artifact of coordinates had not yet been firmly secured. Even general relativity itself had not fully settled into the working habits of astronomy. The theory was admired, yes. And after the 1919 eclipse observations, Einstein became internationally famous. But fame is not the same as comprehension. A theory can be celebrated while its deepest consequences remain uneasy, half accepted, and dimly understood. Einstein himself occupies one of the most fascinating positions in this phase of the story. He had created the theory that made such extreme structures thinkable, and yet he did not move eagerly toward accepting them as natural realities. That tension is often flattened into a simple anecdote, as though Einstein were merely wrong and the future corrected him. The truth is more interesting than that. He shared, in a refined form, the broader hesitation of a scientific community confronted by a theory whose harshest implications still seemed difficult to believe. A mathematically severe possibility did not automatically deserve physical trust. In 1939, Einstein published a paper arguing that realistic distributions of matter would prevent collapse to what we would now call a black hole. The details of that argument belong more fully to the next movement of our story, where gravitational collapse enters the picture directly. But the psychological significance already belongs here. Einstein's reluctance was not trivial. It reflected a real historical condition. The physical meaning of singular behavior in general relativity remained unsettled, and many physicists still felt that nature might somehow avoid the most extreme outcomes implied by the equations. The theory had opened the abyss. Human confidence had not yet caught up. That hesitation tells us something important about scientific discovery. It is not enough to write down correct equations. A community must also learn which consequences of those equations nature should be trusted to realize. Physicists often speak of elegance, inevitability, and simplicity. But beneath those words lies a quieter human process. Some implications feel too abrupt, too severe, too unlike the rest of what one already knows. Before black holes were accepted as physical objects, they carried exactly that emotional charge. They seemed less like ordinary inhabitants of the cosmos than like places where theory itself might be breaking under its own ambition. And yet the equations remained. They stayed on the page, exerting pressure. Schwarzschild's solution could not be ignored forever because it was too central, too clean, too mathematically compelling, even when its strangest feature was not fully understood. It retained the peculiar authority that major results often possess in science. It demanded return. Later physicists would revisit it, reformulate it, and eventually recognize that the troubling behavior at the Schwarzschild radius was not the end of space-time, but something subtler and more physically meaningful. That fuller understanding belongs to a later section. For now, it is enough to feel the long interval before clarity arrived, when the mathematics had already reached into a new region of reality and the imagination of science had not yet fully followed. There is also a broader atmosphere surrounding all of this. The early 20th century was an era in which physics increasingly asked people to believe in realities that could not be approached through ordinary sensory intuition. Electrons, radiation, space-time curvature, and quantum discontinuities all pushed science away from common-sense imagery and toward a disciplined trust in inference. In that larger setting, the future black hole was not entirely unique, but it was unique in intensity. An electron was invisible, yes, but it helped explain familiar phenomena. Curved space-time was strange, but it accounted for gravity. A black hole seemed to go further. It proposed a region where the usual language of light, sequence, and location became disturbingly hard to stabilize. So the movement from Michel's dark star to Einstein's equations is not a simple march forward. It is more like a descent into a more demanding kind of difficulty. The old Newtonian speculation had suggested that gravity might create invisible bodies. General relativity transformed that suggestion by changing gravity from force to geometry. Schwarzschild then revealed that the geometry itself allowed a peculiar threshold around a mass, one whose significance was not yet understood, but could no longer be dismissed. The shadow that had appeared too early in the 18th century was beginning to acquire a harder mathematical outline. It was still not an accepted astrophysical object, but it had ceased to be merely a philosophical curiosity. And once that outline existed, another question became harder to avoid. If relativity permitted such extreme configurations, could actual stars in the real universe ever approach them? Could matter, under the weight of its own gravity, continue inward far enough to test the harshest implications of Einstein's theory? Those questions would pull the story away from pure geometry and toward stellar life, stellar death, and the calculations of a young astrophysicist who was willing to follow collapse farther than many of his elders could comfortably imagine. Once Einstein's equations had made room for gravity to curve reality itself, a new question began to press more firmly on the scientific imagination. It was no longer enough to ask what the mathematics allowed in principle. One had to ask what actual stars, in the real universe, might do when their lives approached their end. Could matter truly be driven so far inward that the most severe implications of relativity would cease to be abstract? Or would nature, somehow, stop short? The answer did not first emerge from a dramatic observation in the sky. It began, instead, in calculation, in the work of a very young physicist who was willing to follow the logic of stellar death farther than many older and more established minds found comfortable. Subrahmanyan Chandrasekhar was only 19 when he left India for England in 1930. traveling by sea to begin graduate work at Cambridge. The journey itself has acquired an almost symbolic place in the history of science, because it was during that voyage that he continued thinking through a problem that would define the early part of his career. The setting could hardly have been more distant from the quiet rooms in which later generations imagined theoretical breakthroughs unfolding. He was a young man crossing oceans, carrying notebooks, papers, and the burden of intellectual ambition, while Europe, and with it British science, still stood as one of the world's central stages for physics. He arrived not as an outsider to thought, but as someone already deeply formed by mathematics, already prepared to inhabit difficult abstractions with unusual seriousness. The question he was pursuing emerged from one of the great discoveries of early 20th century astrophysics: white dwarf stars. These were objects of extraordinary density, the compact remains of stars that had exhausted much of their ordinary fuel. Sirius B, the faint companion to Sirius, had become one of the most famous examples. Here was a body with roughly stellar mass compressed into something close to the size of Earth, matter packed to an extent that defied older intuitions about what a star should be. White dwarfs were not merely curiosities. They were evidence that stellar life did not end in a single uniform way. A star could die into a state so dense, so compact, that familiar categories began to fray. By the late 1920s, a crucial piece of physics had been brought to bear on these objects: quantum mechanics. Still young and dazzlingly incomplete in many respects, offered a new explanation for how white dwarfs could support themselves. The key idea involved electron degeneracy pressure. In ordinary matter, pressure often arises from thermal motion. Particles move, collide, and resist compression. But in a white dwarf, quantum rules impose another kind of resistance. Electrons cannot all be squeezed into the same low-energy states. As matter is compressed, that restriction creates a pressure that does not depend in the ordinary way on heat alone. It is a strange, deeply quantum support system, one of the earliest signs that the final stages of stellar life would be governed by laws far removed from everyday experience. For many physicists, that result was already astonishing enough. It showed that dead stars could be held up by quantum mechanics, by a kind of pressure born not from temperature or chemical change, but from the statistical structure of matter itself. Chandrasekhar looked at the same problem and asked a harsher question. What happens if the star is heavy enough? What if the inward pull of gravity grows so strong that even this quantum resistance begins to face its limit? This was a subtle and dangerous shift in perspective. It required not only technical skill, but a certain temperament, a willingness to distrust the comfort of a partial explanation and push the equations into a more extreme regime. During that sea voyage and in the work that followed, Chandrasekhar combined the physics of degeneracy pressure with special relativity. As the electrons inside a white dwarf are forced into higher and higher momenta, their behavior cannot remain purely non-relativistic. If the star becomes sufficiently massive, relativity begins to matter. And when Chandrasekhar included that effect carefully, the conclusion he reached was stark. Electron degeneracy pressure could not support a white dwarf above a certain maximum mass. Beyond that threshold, the star had no stable white dwarf future available to it. There was, in other words, a limit to how gently a star could die. That mass, now known as the Chandrasekhar limit, is about 4 times the mass of the Sun, though its exact value depends on composition and details of the model. Today the phrase is standard. almost familiar to students of astrophysics. At the time, its meaning was far more disturbing. It implied that white dwarfs were not the universal endpoint for stellar remnants. Some stars, by the simple fact of being too massive, would be forced beyond that state. They would have to go on towards something denser, stranger, and more difficult to picture. Chandrasekhar had not yet produced a modern black hole. He had done something equally important for the history of the idea. He had shown that the life cycle of real stars might carry nature toward domains where ordinary stability failed. This is the point where the emotional atmosphere of the story changes. Up to now, black hole history has unfolded largely through geometry and conceptual possibility. Michel imagined an invisible star. Einstein's theory made severe curvatures thinkable. Schwarzschild uncovered a space-time structure whose implications remained uncertain. But Chandrasekhar moved the problem into the heart of astrophysics. He connected extremity to actual stars, not to hypothetical objects in the abstract, but to bodies that formed, shone, aged, and died. The question was no longer whether a strange mathematical threshold existed. It was whether nature, through stellar evolution, was actively driving matter toward it. Chandrasekhar was especially suited to that kind of work. Accounts of his life, and his own later reflections, reveal a mind of unusual discipline and range. He was methodical, exacting, and often intensely self-contained. He could spend years on a problem, moving through it with patience rather than flourish. His style was not built around intellectual theater. It was built around fidelity to the mathematics. There is something psychologically revealing in that, because black hole history repeatedly depends on people willing to trust formal reasoning, even when the destination feels inhospitable. Chandrasekhar belonged to that class of thinker. He did not seem driven by a taste for provocation. He was driven by the internal demand that a problem be followed through honestly. Cambridge, however, was not merely a place of abstract inquiry. It was also a place of hierarchy, prestige, and scientific personality. And standing near the top of that hierarchy was Sir Arthur Eddington, one of the most celebrated astrophysicists in the world. Eddington had played a central role in making Einstein famous in the English-speaking world after the 1919 eclipse expedition. He was brilliant, eloquent, and widely admired, not only for technical achievement but for intellectual style. He possessed authority in a way few scientists do, a kind of cultural and institutional weight that shaped the atmosphere around him. In such a setting, a young theorist's calculations did not enter the world neutrally. They entered a social structure. At first, Chandrasekhar's work was not ignored. On the contrary, it was recognized as important and sophisticated. But recognition is not the same as acceptance. The deeper implication of the limit, that stars above a certain mass could not simply settle into the known compact state, led directly toward a question many physicists found unsettling. If a white dwarf could not remain stable, what then? At the time, neutron stars had not yet taken on their later secure place in astrophysics, and the broader theory of stellar collapse was still immature. Chandrasekhar's calculations seemed to point toward a future for stars that had not yet been made physically habitable in the communal imagination. They suggested that there were deaths too severe for the existing picture of stellar evolution. Eddington, in particular, resisted the conclusion. Part of that resistance was scientific. He did not accept that nature would permit a star to continue collapsing into what seemed an absurd or pathological state. Part of it was aesthetic and philosophical in a broader sense, though one has to be careful not to dramatize this too crudely. Eddington was not merely defending comfort against truth. He had a powerful intuition for physical plausibility, and he was not prepared to concede that a mathematically derived instability must correspond to a real cosmic outcome. But for Chandrasekhar, the logic was difficult to evade. Once relativity entered the physics of degenerate electrons, the limit followed. And once the limit followed, the old expectation of white dwarf stability for all stellar remnants could no longer be maintained. Their conflict came to a head in the 1930s, most memorably in 1935 at a meeting of the Royal Astronomical Society. There, Eddington publicly criticized Chandrasekhar's conclusions, questioning both the physical interpretation and, in effect, the wisdom of following the mathematics so far. The episode has often been retold as a simple morality play. Young genius vindicated. Older authority exposed as obstructive. There is truth in that outline, but it can become too clean. Historically, the confrontation was painful precisely because both men were serious scientists, and because the scientific community itself had not yet fully settled the terrain on which they were arguing. Eddington's authority magnified the force of his resistance, but the deeper discomfort was widely shared. Chandrasekhar's result did not merely solve a problem. It opened one still. The human imbalance in the encounter was real. Chandrasekhar was young, foreign, and still establishing himself in one of the most prestigious scientific settings in the world. Eddington was a towering figure, admired and institutionally secure. Public disagreement under such conditions does not feel like a purely abstract exchange of ideas. It carries pressure, tone, and consequence. Later accounts suggest that the episode wounded Chandrasekhar deeply. One should be careful not to invent private feelings beyond what the record supports. But it is clear that the resistance affected him. He had arrived at a conclusion through rigorous reasoning, and instead of seeing the field reorganize itself around the new insight, he found that one of the era's most respected astrophysicists was publicly unwilling to follow the argument where it led. There is a broader lesson here about the psychology of science. Data and equations do not enter empty space. They enter communities of taste, training, loyalty, and expectation. A beautiful result can be resisted, not because it is careless, but because it asks too much of an existing worldview. Chandrasekhar's limit did exactly that. It forced astrophysics to accept that stellar death might be divided by a line of mass, and that beyond that line, the universe might drive matter into conditions far more extreme than familiar models had allowed. For many scientists, that was not simply a technical revision. It was a challenge to a whole emotional picture of how nature ought to behave, and yet the force of the calculation remained. One of the remarkable features of Chandrasekhar's story is that he did not become a public crusader for a sensational future state of stars. He did not turn himself into a prophet of cosmic catastrophe. Instead, he continued to work with great range and seriousness across astrophysics, radiative transfer, stellar dynamics, hydrodynamic stability, and later general relativity. This breadth can make his role in black hole history seem, from a distance, less dramatic than it really was. But in a deeper sense, it makes his contribution more compelling. He was not trying to force nature into extremity for its own sake. He was trying to understand stellar structure with precision, and precision itself carried him toward a hard conclusion. In hindsight, Chandrasekhar's limit became foundational because it marked a boundary in the life of stars. Below it, a certain kind of quantum-supported remnant could endure. Above it, that path closed. The universe did not promise a stable white dwarf for every dying star. Mass mattered, and beyond a certain point, it mattered decisively. Even before the full theoretical landscape of neutron stars and relativistic collapse had been clarified, Chandrasekhar had already established something crucial. There were stellar deaths that could not be accommodated within the old equilibrium picture. Stability was conditional. Nature had thresholds. That idea, thresholds in the fate of stars, transformed the moral atmosphere of astrophysics. It introduced a sharper sense of destiny into stellar evolution. A star's end was no longer just a dimming or cooling. It was a question of whether matter could hold itself up against gravity at all. For lighter remnants, one answer emerged. For heavier ones, the answer darkened. Once astrophysicists began to take that seriously, the route toward more extreme, compact objects could no longer be treated as an eccentric side path. It became part of the internal logic of stellar life. A star was not simply a light source. It was a struggle between outward support and inward collapse. And that struggle did not always end in balance. In a way, Chandrasekhar's insight also reshaped the meaning of Einstein's theory. General relativity had already supplied the geometric possibility of severe gravitational structures. But possibility alone can remain suspended, detached from the ordinary processes of the cosmos. Chandrasekhar brought the issue down into the life cycle of real stars. He made collapse thinkable as an astrophysical destiny rather than a purely formal endpoint. He did not yet show exactly how matter would continue inward, nor did he settle the later question of what object would emerge. But he made it much harder to believe that nature would always find a mild solution. Eddington's resistance, seen in that light, becomes even more revealing. He was defending more than a technical preference. He was resisting a universe in which stars might be pushed past the edge of known equilibrium into states that felt, at the time, almost intolerably strange. That does not make him foolish. It makes him historically legible. Scientific communities do not accept conceptual harshness immediately. They need time, alternative models, new calculations, and often a generational shift in sensibility. Chandrasekhar was early, not as early as Michel, perhaps, but early enough to encounter the friction that often greets ideas whose logic outruns the comfort of their age. There is a quiet courage in that sort of intellectual timing. To be too early is not simply to be correct before others. It is to occupy an awkward interval in which your argument is visible, serious, and still not welcomed. Chandrasekhar lived in that interval. He had shown that a white dwarf has a mass limit. He had shown that relativity changes the stability of degenerate matter in a decisive way. He had, in effect, forced open the question of what happens when a star is too massive to stop, where known stellar theory once hoped it could stop. That question would not go away, no matter how uneasy it made the field feel. And once it was opened, physics had to move further. If a sufficiently massive stellar core could not end as a white dwarf, then something else had to follow. Some continued inward fate. Whether through newly proposed compact states or through more radical collapse, the story was no longer content to remain at the edge of instability. It was being drawn, steadily, toward the actual process of gravitational contraction itself. That next step would come in the same year Einstein published his skeptical paper about collapse, 1939, when Robert Oppenheimer and Hartland Snyder would ask, with a new severity, What happens when gravity is finally allowed to continue its work without rescue? Once Chandrasekhar had shown that a white dwarf could not be the final refuge for every dying star, the question sharpened almost painfully. If a stellar remnant was too massive for that quantum-supported state, what happened next? Did nature invent some new form of resistance just in time? Or did gravity continue its work with a severity that earlier generations had only glimpsed in abstract mathematics? By the end of the 1930s, that question had become harder to postpone. Relativity had already opened the conceptual space. Stellar physics had begun to push matter toward the edge. All that remained was to ask, with full seriousness, what continued collapse would actually look like. The answer came in 1939, in a paper by J. Robert Oppenheimer and Hartland Snyder titled On Continued Gravitational Contraction. Even now, the title carries a kind of restraint that feels almost eerie. There is no theatrical language in it, no sense that a cultural icon is about to be born. It reads like a technical investigation, sober and compact. The sort of paper one could easily pass over without suspecting that it contains one of the clearest early foundations of the modern black hole story. That, in a way, is part of its historical character. It did not arrive trumpeting a revolution. It arrived quietly. In the formal language of relativity, while the world around it was sliding toward war, Oppenheimer himself was, by then, already a remarkable figure in American physics, though not yet the public symbol he would later become. He was brilliant, quick, intellectually wide-ranging, drawn to theory with a kind of nervous intensity that many of his students and colleagues would later remember vividly. Hartland Snyder, younger and far less famous, was his student. Together, they chose a model that was intentionally simple, a spherical cloud of pressureless matter, often described as dust, collapsing under its own gravity. The simplicity was deliberate. It allowed them to isolate the logic of gravitational contraction without the full complication of realistic stellar interiors. In modern hindsight, that idealization can look severe, even artificial. But it was precisely this stripped-down clarity that made the calculation so consequential. The result was stark. If the collapsing matter had no internal pressure sufficient to halt the motion, and if one followed Einstein's equations faithfully, the contraction did not stop. From the point of view of an observer riding inward with the collapsing material, the process continued relentlessly. The surface of the star crossed what we would now recognize as the critical radius, and the matter moved onward toward a central singular fate. Yet from the perspective of a distant external observer, the picture looked different. The collapsing surface appeared to slow, to redshift, and to fade, asymptotically approaching the critical boundary without quite crossing it in finite coordinate time. The same event wore two different temporal faces. Depending on where one stood in relation to the collapse, that duality remains one of the most haunting features of black hole physics. And here it appeared with unusual clarity for the first time. For the collapsing matter itself, the journey inward was real and finite. For the distant watcher, the star seemed to freeze at the edge of disappearance. This was not yet the fully matured modern language of event horizons, causal structure, and coordinate choices that later relativists would develop in much greater depth. But the essential drama was already present. Oppenheimer and Snyder had shown that Einstein's theory, when combined with the fate of a collapsing star, did not naturally rescue matter from further descent. It allowed continued contraction all the way down. It is worth pausing here. because this is one of the places where the history of black holes changes tone. Michel had imagined an invisible star. Schwarzschild had uncovered a geometry with troubling features. Chandrasekhar had shown that some stellar remnants could not remain white dwarfs. But Oppenheimer and Snyder did something more direct. They turned collapse into an actual process inside relativity. They did not merely say that an extreme configuration might exist. They described a pathway by which nature, starting from an ordinary enough astrophysical problem, could reach it. In that sense, their 1939 paper is one of the strongest candidates for the true beginning of the modern black hole, not yet in name, but in formation theory. And yet, historically, this beginning did not behave like a beginning at all. The paper did not launch an immediate new era of black hole physics. It did not produce a field crowded with researchers racing to extend the result. It did not transform public imagination, or even scientific consensus, overnight. Instead, it appeared and then, for a time, receded into the background. Later historians of physics have repeatedly returned to this fact with a kind of astonishment. The conceptual importance of the work is now obvious. Its contemporary impact was much quieter. That contrast is one of the most revealing elements in the whole story. Science does not always recognize the full meaning of its own breakthroughs while they are happening. Part of the explanation is historical in the most direct sense. The paper was published in 1939, the year the Second World War began. Europe was collapsing into catastrophe, and the scientific world, especially in physics, was about to be reorganized by war work, forced migration, state power, secrecy, and the race toward nuclear weapons. In such a world, even a brilliant result about gravitational collapse could fail to command sustained attention. The intellectual climate narrowed. Priorities shifted. Whole communities were absorbed into urgent projects whose scale and consequences dwarfed almost everything else. A theory about the final fate of stars, however profound, was badly timed. Oppenheimer's own career embodies that shift with unusual clarity. Within a few years, he would become centrally involved in the wartime effort that led to the Manhattan Project and the atomic bomb. The scientist who had helped clarify one of the most severe implications of Einsteinian collapse would soon be drawn into a very different historical drama, one concerned less with stars than with human destruction, state power, and the politics of survival. It is difficult not to feel the irony. In 1939, he was tracing the death of massive stars into regions from which light could not return. Soon afterward, he would be helping build weapons whose flash would remake the moral landscape of the 20th century. The gravitational problem did not disappear, but his attention and the world's moved elsewhere. There were scientific reasons. 2, for the muted reception. The relativistic community was still relatively small, and many physicists continued to regard the most extreme implications of general relativity with suspicion or unease. The Oppenheimer-Snyder model used pressureless dust, an idealization that made the mathematics tractable, but also gave skeptics room to wonder whether realistic stellar matter would behave differently. That concern was not irrational. Simplified models are powerful, but they always invite the question of how much of their conclusion survives contact with the messier conditions of nature. For a field already uncomfortable with singular collapse, the idealized character of the model made it easier to postpone full acceptance. Then there was Einstein himself, whose 1939 paper argued against the physical realization of such collapse. His resistance did not settle the matter. but it contributed to the broader atmosphere in which the harshest consequences of relativity still lacked communal security. If Einstein was unconvinced that nature truly permitted these objects, that alone was enough to slow the confidence with which others embraced them. It would be too simple to say that black holes were delayed merely because the field failed to understand Oppenheimer and Snyder. They were delayed because the calculation entered a world still struggling to decide how literally Einstein's theory should be read at its outermost edge. This is part of what makes the paper so psychologically interesting. Oppenheimer and Snyder did not write like iconoclasts announcing an impossible truth. The tone is controlled, sparse, almost austere. They follow the mathematics and let it speak with minimal ornament. There is something deeply characteristic of serious theoretical work in that style. The most radical implications are often presented in the calmest language. But this restraint may also have contributed to the paper's strange historical afterlife. It did not advertise itself as the birth certificate of a new cosmic object. It simply showed, with unsettling clarity, that under Einstein's equations, continued gravitational contraction was possible. The world would need time to realize how much was contained in that result. Later generations, looking back, often see Oppenheimer's pre-war work on collapse as one of those moments when an idea becomes technically real before it becomes culturally real. The concept had not yet acquired the stabilizing language it would later need. There was no agreed term black hole, the fuller interpretation of the critical boundary, as something more subtle than a physical singularity in the coordinates, still lay ahead. The astrophysical ecology of compact remnants was not yet fully mapped, but the essential structure had been shown. A star could continue inward. A distant observer would see fading and freezing near the boundary. Relativity was not forcing the universe to stop at comfort. There is another way to appreciate the paper's importance. It changed the moral atmosphere of gravitational theory. Before Oppenheimer and Snyder, one could still imagine that the severe features of relativistic geometry might remain largely formal, or that actual stars would never quite encounter them. After their work, that position became harder to sustain. Collapse was no longer just a suspicious corner of Schwarzschild's solution. It had been connected to stellar evolution with mathematical discipline. A real astrophysical process now led toward the very threshold that earlier theorists had hesitated to inhabit. The modern black hole was not yet socially secure inside science, but it had become much more difficult to keep it at arm's length. At the same time, the paper's temporary neglect reveals something broader about the history of ideas. Important truths do not always spread in proportion to their conceptual depth. They depend on timing, on social readiness, on whether a community has the language and emotional tolerance to absorb them, and on whether history allows people the leisure to notice. Oppenheimer and Snyder had the misfortune of being correct at the edge of world crisis. Their result entered a scientific culture about to be interrupted, redirected, and militarized. For decades afterward, black holes would continue to struggle for full acceptance. And when the concept later rose again, many people would forget how much of the essential collapse story had already been written in 1939. That partial forgetting has had an odd consequence. Oppenheimer is now remembered overwhelmingly for the bomb, for Los Alamos, for state secrecy, for moral conflict in the nuclear age. In popular memory, his place in the history of black holes is often secondary, almost incidental. Yet in the internal history of gravitational collapse, his role is foundational. Before he became an emblem of atomic modernity, He helped produce one of the clearest early demonstrations that Einstein's theory permits the irreversible collapse of massive stars. That older Oppenheimer, the pre-war theorist following gravity into darkness, can feel almost hidden behind the later legend. The same is true, in a different way, for Snyder. History often condenses itself around famous names. But this paper was a collaboration, and Snyder's place in it deserves to be seen clearly. Hartland Snyder was not the architect of a vast later school of black hole theory, nor did he become a lasting public symbol. Yet he was there at the key moment, helping shape a result whose later significance would only continue to grow. The history of science often contains such figures, indispensable at a decisive point, then partially eclipsed by the reputations around them. Their work survives even when their names become quieter. In another sense, the paper also marks a turning point in how science learned to handle invisibility. Michel had imagined dark bodies whose presence might be inferred. Schwarzschild had found the geometry around a mass. Chandrasekhar had shown that some stars must go beyond white dwarf stability. Oppenheimer and Snyder fused these lines into a temporal drama. They showed not just that there could be a strange object, but that an ordinary enough star, under the right conditions, could become one through a lawful process of continued contraction. That made the unseen far more concrete. The darkness now had a history. It was no longer merely a theoretical endpoint. It had a route. Still, the route remained conceptually difficult. The outer boundary in the calculation continued to look peculiar. From far away, collapse seemed to slow indefinitely. From within, the motion continued. Such split descriptions invited confusion, especially in a field that had not yet developed the mature language of horizons and coordinate systems that would later clarify matters. In that sense, the paper was both a breakthrough and a source of further unease. It revealed the process, but it did not yet provide the community with all the interpretive tools needed to live comfortably inside what had been revealed. That work would come later, through new formulations and a patient rereading of the geometry itself. So, Section 4 in the history of black holes is shaped by a paradox. One of the decisive early theoretical foundations appeared in plain sight, published in a leading journal, written with clarity, and yet it did not immediately become the center of a new field. It was both a beginning and, for a time, a kind of disappearance. The idea had arrived, but the world was elsewhere. The equations had spoken, but history had raised its own louder voice. Few moments capture more clearly how science unfolds inside time rather than outside it. And because the full conceptual meaning of collapse was still not settled, because the strange outer boundary still looked confusing, because the language needed to make these objects feel physically intelligible had not yet fully formed, the story could not stop here. The next phase would require physicists to return to Einstein's equations with a different kind of patience, not to ask whether collapse could continue, but to understand more clearly what sort of boundary the collapsing star was actually creating, and how an object that once looked like a paradox might begin to look like a genuine inhabitant of the universe. The route toward collapse had been written down, but the destination still looked strangely unstable in the mind. Oppenheimer and Snyder had shown that continued gravitational contraction was permitted, even natural, under Einstein's theory. Yet the object at the end of that process did not feel fully settled inside physics. It still hovered between mathematics and interpretation, between formal possibility and physical intuition. The outer boundary around the collapsing star remained especially troublesome. To many readers, it still looked like a place where the equations themselves were becoming sick. And as long as that was true, the emerging black hole could be pushed back into a familiar category, not as a genuine inhabitant of the universe, but as a pathology in the formalism. That tension is essential to this phase of the story, because science was now dealing with something more delicate than a new result. It was dealing with a result that had to be read correctly. The difference mattered enormously. A strange feature in an equation can either reveal a new structure in nature or expose a weakness in the coordinates used to describe it. For years, the Schwarzschild radius sat uneasily between those possibilities. Physicists knew it marked something important, but many were not yet sure what kind of importance it was. If the apparent singularity at that radius was only a coordinate artifact, then the mathematical shock it produced could not be taken at face value. But if the deeper geometry remained intact through that boundary, then the older fear that relativity had merely broken down there would have to give way to something much more unsettling. It took time, and a more mature generation of relativists, for that reinterpretation to become clear. One of the crucial figures in this change was David Finkelstein. In 1958, he reformulated the Schwarzschild solution in a way that made the causal structure easier to see. What earlier coordinates had made look pathological at the critical radius turned out not to be a true physical singularity at all. The real singularity, in the sense of a deeper breakdown of space-time, lay at the center. The radius around the collapsing object marked something different, a one-way surface, a boundary across which signals could enter, but from which they could not return. In modern language, this was the event horizon. At the time, the importance of this reinterpretation was profound. The paradox had not vanished. It had changed character. Physics. APS. Org. This kind of change can seem abstract when summarized too quickly, so it helps to linger on what it meant psychologically. For decades, the Schwarzschild boundary had frightened many physicists because it looked like a place where the theory itself might fail. Finkelstein's work suggested something subtler and, in a way, more difficult to domesticate. The theory was not failing there. The geometry was doing something extreme, but lawful. The troubling surface was not a wound in the mathematics. It was a feature of the world the mathematics had been trying to describe. A collapsing star, viewed correctly, was not crashing into an error. It was creating a region of space-time with a new causal logic. Physics. APS. Org. That shift altered the emotional texture of black hole history. Earlier stages had often been haunted by the suspicion that these objects were artifacts of overzealous formalism, cases where theorists had followed equations beyond the point where nature intended them to go. After Finkelstein, that suspicion became harder to maintain. The boundary was still severe, still conceptually strange, but it no longer invited dismissal in quite the same way. Physics was learning, slowly, that the object at the end of gravitational collapse might have to be taken on its own terms. The event horizon was not a theatrical flourish. It was the sign that space, time, and causality had been reorganized by gravity so strongly that ordinary intuitions about escape and sequence no longer applied. There is a pattern here that appears often in the history of science. Sometimes a discovery does not require brand new data. It requires a new reading of something already known. The equations had been present for decades. Collapse had been worked through before the war. What was missing was not formal material, but interpretive clarity. Science had to learn how to see what the mathematics had been saying all along. This is one reason the black hole story feels so different from many other scientific narratives. It did not advance simply from observation to theory or theory to experiment. It advanced through a repeated labor of conceptual reorientation. Physicists had to train themselves to inhabit a geometry that did not feel natural at first. Once that reinterpretation began to settle in, another kind of transformation became possible. An object that had previously sounded like a contradiction could start to sound like a legitimate physical entity, but it still lacked something important. It lacked a stable place in scientific language. Naming matters in science more than outsiders sometimes realize. A good name does not merely label an object. It helps gather scattered intuitions, results, and arguments into a single conceptual focus. Before black holes had their eventual name, they moved through the literature under phrases that were accurate but cumbersome. Phrases like completely collapsed gravitational object, or descriptions even more awkward than that. Such language carried information, but it did not carry force. This is where John Archibald Wheeler enters the story with unusual significance. Wheeler was one of the great theoretical physicists of the 20th century, but he was also something rarer, a builder of conceptual worlds. He had a gift for language, for giving abstract structures names that made them memorable without trivializing them. He worked on nuclear physics, gravitation, quantum theory, and the broader philosophical implications of physics. And across these domains, he showed a special sensitivity to the way words can stabilize thought. By the late 1960s, the phrase black hole began to circulate more decisively, and Wheeler played the central role in making it stick. The exact prehistory of the phrase is a little untidy, as such histories often are. Robert Dickey may have used it informally earlier, and others may have spoken it before Wheeler made it public. But Wheeler was the figure who truly popularized it and helped turn it into a durable scientific term. Princeton. EDU. That achievement was not superficial. Black hole condensed a long and difficult story into 2 words that immediately suggested both invisibility and confinement. The phrase gave the object psychological reality. It invited both specialists and non-specialists to imagine that they were dealing with something unified, something no longer dispersed among technical descriptions and interpretive caution. It is one of the ironies of science that a name can arrive late in a concept's development and yet feel, in retrospect, as though it had been waiting there from the beginning. Wheeler understood something important about intellectual life. If an idea is to endure and circulate widely, it must often become speakable before it becomes fully thinkable. Wheeler's role in black hole history extends beyond naming, though the naming alone would have been enough to secure his place. He was one of the central figures in mid-century American relativity, and his influence helped bring a field that had once seemed mathematically elegant but somewhat peripheral into closer dialogue with mainstream theoretical physics. General relativity, after all, had lived for decades in an odd position. It was foundational and prestigious, yet in certain periods it felt marginal compared with the rapid development of quantum mechanics, nuclear physics, and particle theory. Wheeler helped create an atmosphere in which the study of extreme gravitational objects felt like living physics again, physically meaningful, conceptually rich, and worthy of deep sustained attention. If Finkelstein helped clarify the meaning of the horizon, Wheeler helped create the culture in which such objects could finally be discussed without embarrassment. That matters because scientific acceptance is never purely logical. Communities need language, confidence, and shared frameworks of interest. Without them, even correct ideas can remain oddly homeless. Black holes had long lived in that condition. Now, gradually, they were beginning to acquire citizenship within physics. And just as that was happening, another mathematical breakthrough made the emerging object more realistic than the old idealized picture had ever been. The Schwarzschild solution described a non-rotating spherical mass. It was clean, central, and conceptually powerful. But in the actual universe, almost nothing of astrophysical interest is perfectly still. Stars rotate. Matter carries angular momentum. Collapse, in nature, would almost never proceed in exact spherical purity. If black holes were to become believable as actual astrophysical products, relativity needed a solution that could accommodate rotation. In 1963, Roy Kerr provided it. His exact solution for the space-time around a rotating mass changed the field profoundly. And to Wikipedia.org, the Kerr solution is one of those results in physics that carries both technical depth and aesthetic shock. It did not merely tweak the old picture. It revealed that rotating black holes possessed a much richer structure than their non-rotating counterparts. There was still an event horizon, but there was also an ergosphere, a region outside the horizon where space-time itself was dragged around by the spinning mass so strongly that no observer could remain stationary with respect to infinity. Rotation did not simply decorate the object. It transformed the surrounding geometry. Black holes were no longer just dark static endpoints. They were dynamic, structured, physically more plausible inhabitants of the universe. This mattered for several reasons at once. First, it made black holes feel less like mathematical curiosities, constructed under unrealistically pristine assumptions. A rotating solution was much closer to what actual collapsed stars might produce. Second, it opened new physical possibilities. Energy extraction, frame dragging, and more complex orbital behavior could all now be studied in a serious way. Third, the sheer elegance of the Kerr geometry helped persuade theorists that these objects belong to the inner coherence of general relativity, not to its accidental fringe. There is an aesthetic dimension to scientific conviction that is sometimes misunderstood from the outside. Beauty does not prove truth, but in mathematics and theoretical physics, certain kinds of beauty can be signs that a structure is too deep, too internally consistent, to be ignored lightly. Few people felt that aesthetic force more strongly than Chandrasekhar. In his later work, he wrote about the Kerr solution with a kind of restrained wonder. This is one of the quiet continuities in the black hole story. Chandrasekhar, who as a young man had shown that some stars could not end as white dwarfs, now lived long enough to see the theoretical architecture of the more extreme alternatives become richer and more exact. His early calculations had forced open the question. Later generations, and later Chandrasekhar himself, would find that the answers were embedded in a geometry more beautiful and more severe than the field had once imagined. By this stage, the object at the center of our story had undergone a profound transformation. What had once seemed like a suspicious edge in Schwarzschild's coordinates was now understood as a horizon with causal meaning. What had once been described in awkward phrases was now widely called a black hole. What had once depended on stillness and symmetry now possessed a realistic rotating form. Step by step, the conceptual barriers had thinned. The paradox had not been eliminated. Black holes remained deeply strange, but the strangeness had become physically intelligible rather than merely pathological. This is a subtle but decisive difference. Physics can live with strange things. It can live with time dilation, wave-particle duality, and expanding space-time, what it cannot easily live with, at least for long, are things that seem both important and unintelligible. The middle decades of black hole theory were spent converting unintelligibility into intelligibility. Finkelstein helped show that the horizon was not a sign of theoretical collapse. Wheeler helped consolidate the object through language and institutional attention. Kerr demonstrated that the geometry of these collapsed objects could reflect the rotational realities of actual astrophysical bodies. Together, these developments did not make black holes ordinary. They made them inhabitable as ideas. And once an idea becomes inhabitable, inquiry deepens. Physicists could now ask more than whether collapse was possible. They could ask what kind of object emerged, how it behaved, what features it retained, what energy processes might surround it, what role rotation played, and how such an object might announce itself indirectly through its effect on nearby matter. This new stage of thinking did not yet amount to observational confirmation, and one must be careful not to let hindsight rush the pace. Black holes were still, for many scientists, somewhat provisional as astrophysical realities. But the tone had changed. They were no longer embarrassments in the equations. They were candidates for genuine physical existence. There is another important psychological shift here. Early resistance to black holes had often come from a feeling that nature would somehow avoid such extremes. That instinct weakens when each new theoretical advance removes another reason for avoidance. First, the collapse route exists. Then the horizon becomes interpretable. Then the object gains a name. Then a rotating version appears that looks far more like what astrophysical processes would actually produce. At a certain point, the burden of disbelief begins to move. One no longer asks so easily, why should nature allow this? One begins, more quietly, to ask, why should nature avoid it? That reversal prepared the field for an even more far-reaching change. Once black holes became conceptually secure enough to be treated as real theoretical objects, they also became fertile ground for deeper questions about gravity itself. Were they rare accidents or generic outcomes of collapse? Were singularities artifacts of special symmetry or unavoidable consequences under broad conditions? Did these strange regions expose the limits of Einstein's theory or the depth of it? Those questions would soon be taken up by a mathematician with a gift for seeing geometry at its most severe, Roger Penrose, and by a younger theorist who would help turn black holes into one of the central paradoxes of modern physics. By the time black holes had become conceptually inhabitable, physics had crossed an important threshold. The object no longer seemed like a sickly corner of the equations, or a merely embarrassing endpoint that one might politely avoid. The horizon could be interpreted. The language had improved. Rotation had entered the picture. And yet a deeper uncertainty remained. Were these objects rare mathematical curiosities that required exquisitely special conditions? Or did Einstein's theory drive toward them with a harsher kind of generality? That question would be taken up by Roger Penrose, whose work changed the status of black holes from plausible to difficult to evade. Penrose came to the problem with a style of mind very different from the older generation's hesitations. He was deeply geometric, drawn to structure, topology, and the underlying logic of space-time itself. Where earlier discussions of collapse had often depended on symmetry, idealization, or highly specific models, Penrose asked whether the tendency towards singular collapse could be shown under much broader conditions. That shift in emphasis was decisive. It meant moving away from the thought that black holes might be artifacts of unusually neat examples, and toward the possibility that they were built into the very grammar of general relativity. In 1965, Penrose published his singularity theorem, introducing the crucial concept of a trapped surface. Once such a surface formed during gravitational collapse, the theorem showed, and given reasonable energy conditions, the continued development toward a singularity could not be avoided within classical general relativity. The force of that result lay in its breadth. It did not depend on the perfect spherical symmetry of older toy models. It suggested that the severe fate glimpsed earlier was not a fragile mathematical accident, but a robust feature of Einstein's theory. The Nobel Committee would later summarize Penrose's achievement in exactly those terms, as the discovery that black hole formation is a robust prediction of general relativity. That phrase, robust prediction, matters more than it first appears to. It marks a change in the burden of doubt. Earlier, a skeptic could always say that extreme collapse depended on oversimplified assumptions, on unreal stars, or on formal peculiarities that nature would never honor. Penrose weakened that refuge. His theorem did not tell physicists every detail of what a realistic collapsing object would look like, and it did not solve every interpretive problem around singularities. But it made it much harder to believe that careful adjustments in the initial conditions would always spare the universe from these extreme outcomes. The geometry had become stern. There is an austere beauty in that stage of the story. Science often advances by narrowing uncertainty, by replacing a large fog with a smaller one. Penrose did something more unsettling. He reduced one kind of uncertainty while exposing another. If singular collapse was indeed generic under broad conditions, then black holes were no longer the main conceptual shock. The shock moved inward, toward the singularity itself, toward the place where classical spacetime seemed to fail, general relativity. The theory that had so magnificently described gravity was now pointing toward regions where its own classical language could no longer be trusted to remain complete. That is why Penrose's work did more than make black holes respectable. It made them philosophically dangerous. They became places where one could no longer separate astrophysics from the deeper structure of physical law. If collapse naturally generated singular behavior, then black holes were not merely exotic stellar remnants. They were laboratories of the extreme, places where the limits of Einstein's theory became impossible to ignore. The object that earlier scientists had resisted because it seemed too strange was now becoming indispensable precisely because its strangeness revealed the edge of what fundamental physics could currently explain. Penrose did not stop at theorem proving alone. In the years that followed, he explored related questions that would shape the field for decades, including the possibility that singularities might sometimes be naked, visible in principle rather than safely hidden behind horizons. That prospect was alarming enough that Penrose proposed what became known as cosmic censorship, the conjecture that nature somehow prevents such exposed singularities from arising in realistic settings. Even today, the status of cosmic censorship remains subtle and unresolved in full generality. That unresolved edge is part of what makes this phase of black hole history so rich. Penrose had made collapse harder to deny, but in doing so, he had also opened a new frontier of uncertainty around what the universe is willing to hide. If Penrose brought severe geometric discipline to the field, Stephen Hawking would bring something else. A distinctive combination of boldness, speed, and comfort with paradox. Hawking's early work was deeply shaped by Penrose's methods, And in the late 1960s and early 1970s, he extended singularity theorems into cosmology and the global structure of space-time. Here again, black holes were part of a wider intellectual shift. The same techniques that clarified collapse could also be turned toward the origin of the universe itself. Singularities were no longer special embarrassments confined to a few pathological solutions. They seemed woven into the large-scale logic of relativistic gravity. Hawking's personal style mattered here. Biographical accounts and recollections from colleagues repeatedly emphasize his competitiveness, his wit, and his appetite for deep, difficult questions. He was also unusually comfortable working with visual and geometrical intuition, a useful trait in a field where the global structure of space-time mattered as much as local calculation. His physical illness, progressing through the years in which his scientific reputation was rising, is inseparable from public memory. But it should not flatten the intellectual point. Hawking mattered because he had the kind of mind that did not back away when a theory began to produce contradictions or severe implications. In black hole physics, that temperament would become decisive. For a time, the new atmosphere around black holes remained mostly classical. These objects were severe, but they were still understood within general relativity as one-way systems. Matter and radiation could fall in. Nothing could escape. That picture had a certain harsh simplicity. And by the early 1970s, many physicists were beginning to explore it with growing confidence. Then another thinker, Wittgenstein, proposed something that sounded almost improper. He suggested that black holes should have entropy, and that this entropy should be proportional to the area of the event horizon. To see why this was so provocative, it helps to remember what entropy meant in physics. Entropy was not just a numerical label. It was a measure tied to thermodynamics, disorder, and the counting of microscopic states. A system with entropy had, in some meaningful sense, internal informational richness. But a classical black hole seemed to erase detail. Once matter crossed the horizon, all the fine-grained distinctions of the material appeared lost to the outside world, replaced only by a few macroscopic parameters such as mass, charge, and angular momentum. How, then, could such an object have entropy in a serious thermodynamic sense? Wittgenstein's suggestion pushed directly against the classical picture, yet it was motivated by an equally serious concern. Without black hole entropy, the second law of thermodynamics seemed endangered when entropy-bearing matter fell into a hole. Hawking initially resisted this idea. That detail is one of the most revealing in the entire story, because it shows how even the boldest theorists do not always recognize which paradox will turn out to be fertile. At first, he did not accept Wittgenstein's thermodynamic interpretation. A classical black hole, after all, emitted nothing. If it had temperature in any ordinary sense, that would imply radiation. And radiation seemed incompatible with the event horizon as then understood. Yet the tension did not go away. It sat there, quietly, as one of those conceptual irritants that physics cannot ignore forever. Then came one of the most astonishing reversals in modern theoretical physics. In 1974 and 1975, Hawking showed that quantum effects in curved space-time imply that black holes are not perfectly black after all. They emit thermal radiation, the horizon. When quantum field theory is taken seriously in the background of curved space-time, is associated with particle creation and a temperature inversely related to the black hole's mass. What had looked like a one-way graveyard in classical relativity became, in semi-classical physics, a glowing thermodynamic object. The critic of black hole entropy had provided the decisive calculation that transformed Bekenstein's daring conjecture into something far stronger. The intellectual shock here is difficult to exaggerate, though it should not be dramatized into theatricality. Black holes had already forced physics to accept severe causal structures, horizons, and collapse towards singularity. Now they were becoming hotter, stranger, and more revealing still. A black hole could radiate, lose mass, and in principle evaporate over immense spans of time. Thermodynamics, quantum theory, and general relativity, three great domains of 20th century physics, were suddenly speaking to one another through an object that earlier generations had struggled even to believe in. Hawking radiation did not merely add one more property to black holes. It changed what they were. There is a pattern here worth noticing. Every time black holes became easier to accept, they also became harder to understand. First, they moved from dubious mathematical pathology to legitimate gravitational endpoint. Then Penrose showed that collapse towards singularity was general enough to be taken seriously. Then Bekenstein and Hawking made them thermodynamic. The object did not become simpler with acceptance. It became more central and more paradoxical. Science was no longer asking only whether black holes exist. It was asking what sort of entity can have horizon area, entropy, temperature, evaporation, and a classical interior that seems to end in singularity. This was also the point at which black holes began to transform the broader culture of physics. They were no longer just about dead stars or unusual space-time solutions. They became crossroads, questions about information, the arrow of time, quantum fields and curved backgrounds, and the ultimate consistency of physical law all began to gather around them. Black holes had started as the darkest objects in the universe. By the mid-1970s, they were also among the brightest sources of conceptual illumination. They exposed the seams between major theories with almost cruel efficiency. Hawking's public image would later become so large that it can distort the internal rhythm of the story. It is tempting to let the narrative rush toward his fame, toward the wheelchair, the voice synthesizer, the symbolic force of a mind confronting the universe under extraordinary personal constraint. But inside the history of black holes, what matters first is something quieter and sharper. Hawking helped turn black holes from extreme endpoints into thermodynamic systems. He helped reveal that the horizon is not merely a boundary of no return. It is also a place where quantum theory becomes impossible to keep outside the conversation. That was the deeper revolution. Bekenstein deserves to remain clearly visible here as well. Scientific memory often compresses itself around the most famous calculation. Yet Bekenstein's leap was indispensable. He was the one willing to say that black holes might have entropy at all, and to tie that entropy to area. Without that conceptual provocation, Hawking's later result would have landed in a different landscape. The relationship between the two men, intellectually speaking, is one of the most beautiful patterns in the history of science. A conjecture that first looks too bold, a skeptic who objects, and then a deeper calculation that vindicates the boldness while transforming it into something even stranger. At the same time, the Penrose-Hawking era did not close the book on singularities or horizons. It intensified the stakes. If collapse toward singularity was generic, and if black holes radiated, then classical spacetime, semi-classical quantum theory, and thermodynamics were all giving partially overlapping descriptions of an object whose full ontology remained unsettled. Were singularities genuine physical entities? or signs that quantum gravity must eventually replace the classical story. What, precisely, was happening to information in evaporation? Could the horizon be treated as a thermodynamic surface without changing something fundamental in how reality was understood? These questions would echo through the next decades of theoretical physics. And yet, for all this richness, one thing still remained incomplete. The black hole had become a mature theoretical object, one that revealed the depth and limits of major physical theories. But it was still, in the eyes of many, more at home in thought than in the sky. The next transformation would require astronomers to learn how to detect the invisible through matter, motion, and high-energy emission, until the objects that had once seemed like severe consequences of formal reasoning began to leave measurable traces in the universe itself. By now, black holes had become mature theoretical objects. They had emerged from geometry, collapse, singularity theorems, and thermodynamic paradox. They had become central to some of the deepest questions in physics. And still, for many scientists, there remained a lingering asymmetry in the story. Black holes were intellectually powerful, but they were still most vivid inside equations. To become fully real in the broader scientific imagination, they would have to leave marks in the sky, not just in thought. The next transformation would come from a different kind of discipline, quieter in its own way, but equally severe: the art of inferring an unseen object from what it does to the matter and light around it. That requirement posed a special challenge. A black hole, by definition, does not present itself directly as a shining body with a surface and a spectrum of its own. It must be detected indirectly, through accretion, orbital motion, high-energy radiation, or some other signature of its gravitational influence. In a sense, this returns the story to an old intuition already present in Michel's 18th century speculation. The invisible might have to be known through the visible companion it disturbs. But the 20th century had new instruments, new wavelengths, and a far more demanding standard of proof. It was no longer enough to suggest that such an object might exist. One had to show, with measurements, that the best explanation of the observed behavior was a compact body too massive and too small to be anything else we knew. One of the decisive new windows opened in X-ray astronomy. X-rays do not penetrate Earth's atmosphere well, which meant that a whole universe of violent, high-energy processes remained largely hidden until the age of rockets and space-based instruments. Once that window opened in the 1960s, the sky began to look different. Compact objects drawing in matter from nearby companions, heating gas to extraordinary temperatures, and releasing powerful X-ray emission started to appear as a new class of source. For black hole history, this mattered enormously. It meant that collapse was no longer only a matter of stellar death in theory. There were now real systems in which something compact and unseen seemed to be feeding on matter and radiating with startling intensity. Among these new sources, Cygnus X1 would become the most famous. It had first been detected as an X-ray source in the 1960s, but the crucial step came when astronomers began to identify its optical counterpart and reconstruct the binary system in which it lived. In 1971, Paul Merton and Louise Webster published the optical identification of Cygnus X1 in Nature, linking the X-ray source to the blue supergiant star HDE 226868. This was not yet the final proof of a black hole, but it was a decisive advance. It turned a mysterious X-ray source into a dynamical problem, a system whose visible star could be studied for signs of motion around an unseen companion. That move from source identification to orbital reasoning was the heart of the method. If the visible star was orbiting something dark, then its motion could reveal the mass of the unseen object. And if that unseen mass came out too large to be a white dwarf, and too large to be plausibly accommodated by a neutron star under known physics, then the old theoretical black hole would begin to look less like a philosophical destination and more like a practical astronomical inference. In 1972, Charles Thomas Bolton refined the analysis of the Cygnus X-1 system and argued that the compact object's mass exceeded the upper limit then considered plausible for a neutron star. That did not instantly silence all doubt, but it changed the tone of the discussion. The object was now widely treated as a black hole candidate, and over time it became the first such candidate broadly accepted by the community. The phrase black hole candidate is worth pausing over because it captures the epistemology of this moment with unusual precision. Astronomers were not claiming that they had photographed a horizon or watched matter cross a causal boundary. They were doing something more disciplined and, in some ways, more revealing about how science often works. They were building a case by exclusion. The compact object in Cygnus X-1 appeared dark. It appeared small. Its gravitational pull, inferred through the motion of its companion, suggested a mass too high for the more familiar compact remnants of stellar evolution. The X-rays indicated accretion onto something intense and compact. None of this was a direct portrait. Together, however, it formed a pattern that increasingly pointed toward one conclusion. This style of evidence could feel unsatisfying to people outside astrophysics, because it lacked the simplicity of direct sight. But science has always advanced by learning how to trust well-constructed indirect arguments. Neptune was not first discovered by a naked-eye revelation, but through perturbations in another planet's motion. Atoms became real long before anyone could image them in anything like a modern sense. Black holes required the same maturity of method. If the object itself could not shine, then its gravitational influence, its accretion physics, and its timing behavior would have to serve as testimony. In that respect, Cygnus X-1 was not only an astronomical breakthrough, it was also a lesson in scientific character, a reminder that reality often has to be approached through traces rather than appearances. There is another reason Cygnus X-1 mattered so much. It brought the black hole into a system that felt physically concrete rather than purely theoretical. Here was a bright star, a compact companion, gas transfer, an accretion flow, and strong X-ray emission. The black hole ceased to be only the endpoint of a collapse theorem or a thermodynamic paradox. It became a participant in an astrophysical environment. Matter spiraled inward. Energy was released. The surrounding system could be measured and monitored. The strange object at the center of decades of conceptual difficulty now had a sky position and a living context. That shift, from abstract endpoint to active cosmic engine, changed the imaginative reality of black holes just as surely as Wheeler's naming had changed their linguistic reality. Even so, caution remained. Astronomers are rarely rewarded for premature certainty, and black hole history by this point had already taught them how easily the severe implications of theory could outpace communal confidence. Cygnus X-1 became widely accepted over time rather than instantly. That gradual acceptance is part of what makes it historically important. It showed the community learning how to treat black holes as operational astrophysical hypotheses. One did not need a direct image to take them seriously. One needed a chain of evidence strong enough that every more familiar alternative looked less convincing. While stellar mass candidates were beginning to stabilize the black hole's status in X-ray astronomy, another, even more ambitious line of thought was taking shape in extragalactic astrophysics. Quasars had been discovered in the 1960s, and their luminosities were so extreme that they demanded an explanation capable of converting matter into energy with extraordinary efficiency. Nuclear burning, so effective in ordinary stars, seemed inadequate for the observed output. The question was severe in a different way from stellar collapse, but it led toward the same object. If matter falls into a deep gravitational potential well before disappearing behind a horizon, a large fraction of its rest mass can be radiated away. Accretion onto a massive collapsed object began to look like a candidate engine for quasars and active galactic nuclei. Donald Lynden Bell played a central role in this transition. In 1969, he proposed that galactic nuclei might be collapsed old quasars, suggesting that the brilliant quasar phase and the quieter massive dark objects in galaxy centers could be related. This was a bold reframing of the problem. Black holes were no longer merely possible remnants of massive stars. They were becoming potential central engines of galaxies, objects with millions or billions of solar masses, capable of powering some of the brightest phenomena in the universe. Lynden Bell's idea opened a much larger scale for black hole thinking. The object once feared as a strange endpoint of collapse was now being asked to explain the behavior of entire galactic cores. Martin Rees, working in the same broad intellectual movement, helped deepen and extend this picture. Along with Lynden Bell, he explored the connection between quasars, dust, and the galactic center in a 1971 paper, and over the years he became one of the most influential voices in arguing that massive black holes could sit at the centers of galaxies and drive observed activity through accretion. Here again, the theoretical move was elegant because it joined several lines of thought at once. Quasar energetics demanded high efficiency. General relativity already admitted severe compact objects. Stellar collapse had made black holes harder to dismiss. Now the same class of objects seemed capable of scaling upward, from the death of stars to the architecture of galaxies. This was a profound widening of the black hole's role in science. Earlier, black holes had been discussed as rare consequences of unusual stellar deaths, mathematically extreme, but perhaps astrophysically marginal. The quasar and galactic nucleus problem pulled them into the center of cosmic structure. A supermassive black hole was not just a dead remnant. It could be an organizer of activity, a source of enormous luminosity when fed by infalling gas, and perhaps even a long-term participant in the life of a galaxy. The invisible object was becoming not only detectable, but generative. It could shape what astronomers actually observed at the largest luminous scales. Still, here too the pattern of evidence was indirect. No one in the late 1960s or early 1970s was imaging horizons and galactic centers. The case had to be built through energetics, variability, compactness, and the consequences of accretion. That is one reason this stage of the story is so instructive. Science was not converting black holes from theory into observation by some single spectacular proof. It was teaching itself, case by case, how to reason toward them from different kinds of data. In X-ray binaries, the crucial clues were orbital mass estimates and compact high-energy emission. In quasars and active nuclei, they were luminosity, size constraints, and the extraordinary efficiency demanded by the source. The The black hole was becoming real through a family of methods rather than a solitary triumph. That diversity of evidentiary paths also changed the standards of belief. A black hole did not need to be seen in the naive sense to count as scientifically credible. It needed to be the most coherent explanation across multiple lines of measurement. That is how many difficult objects in science become real, not by appearing directly in one perfect moment, but by surviving repeated attempts to replace them with something less radical. Cygnus X1 mattered because familiar alternatives began to fail. The quasar problem mattered because more conventional engines could not account for the observed output cleanly enough. Over time, the black hole ceased to be merely one possibility among many. It became the least strained explanation in a growing number of contexts. There was also a cultural shift inside astronomy and physics. Earlier generations had struggled to accept black holes because they sounded like the severe edge of mathematical theory. By the 1970s, that resistance was weakening, in part because the objects were now useful. They organized observations. They made sense of otherwise difficult phenomena. They connected high-energy astrophysics with relativity and with the growing study of galaxies. Black holes were no longer only things one feared or resisted conceptually. They were things one could work with. They entered proposals, models, observing strategies, and scientific debate as practical explanatory tools. That transition, from conceptual burden to productive instrument of thought, is one of the clearest signs that an idea has matured. And yet there was still a distinction to be made between candidates, arguments, and what later generations would call compelling proof. Cygnus X1 was widely accepted as a black hole candidate and became historically central because of that status. The case for supermassive black holes and galactic nuclei was becoming increasingly persuasive as quasar theory advanced. But astronomy had not yet achieved the kind of direct dynamical demonstrations that would later anchor the galactic center story. The black hole was now strongly present in the sky, but often through inference rather than through a single visually decisive observation. That distinction matters because it keeps the history honest. Theoretical maturity had met observational plausibility. The era of overwhelmingly convincing central dynamical evidence still lay ahead. This is why Section 7 feels, in retrospect, like a hinge in the entire documentary. The black hole is no longer mainly an object of severe thought. It is becoming an astrophysical citizen. Astronomers know how to look for it by studying companions, spectra, variability, and accretion. Extragalactic researchers are beginning to treat it as the engine of quasars and active nuclei. The standards of evidence are shifting from can such an object exist, to which observed systems are best explained by one. That is a much more advanced question. It presumes a confidence that earlier generations did not have, and once that confidence existed, the next ambition became possible. If black holes could be inferred from binary motion and from the power output of quasars, then perhaps one day astronomers could measure the motions of stars around a massive, invisible object at the center of our own galaxy, or detect space-time itself ringing after black holes collide, or even trace the shadow cast by light near a horizon. Those later achievements would belong to another era and another level of instrumental patience. But the ground for them was laid here, in the long apprenticeship by which astronomy learned to trust the invisible through its effects. By this stage, the black hole had already passed through many lives. It had been a speculation, a geometry, a collapse process, a horizon, a theorem, a thermodynamic paradox. an X-ray candidate, and a galactic engine. What remained was a final change in tone. The object had to cross from persuasive inference into something closer to lived astronomical reality, not because indirect reasoning was weak, but because the history of black holes had always carried a peculiar burden. Again and again, scientists had been asked to trust something that seemed to withdraw from every ordinary form of encounter. For that long story to feel complete, the universe would have to offer evidence so clean, so patient, and so physically concrete that even the old discomfort began to lose its footing. One of the most important steps toward that new certainty took place, quietly, at the center of our own galaxy, Sagittarius A star, the compact radio source at the Milky Way's core, had been known for decades as a suspiciously energetic and crowded region. But suspicion is not proof, and galactic centers are complicated places. Dust obscures the view in visible light. The stellar environment is dense. The scale is enormous, yet the crucial region is tiny on the sky. To show that a supermassive black hole truly sat there, astronomers needed more than a luminous source or a suggestive theoretical model. They needed to measure gravity at work directly, by tracing how individual stars moved around an invisible central mass. That effort unfolded over decades, and it is one of the great stories of observational patience in modern astronomy. Two teams became central to it, working independently and, at times, competitively. One was led by Reinhard Genzel in Europe, using instruments associated with the European Southern Observatory and the Max Planck Institute for Extraterrestrial Physics. The other was led by Andrea Ghez at UCLA. Both groups pushed infrared astronomy and high-resolution techniques to their limits, because only by working through the dust and achieving exquisite angular precision could they follow individual stars whipping around the galactic center. This was not the kind of discovery that arrives in a single night at the telescope. It demanded years of repeated observation, instrumentation advances, and the willingness to let a star complete enough of its orbit for the geometry of the system to reveal itself. There is something deeply fitting in that method. For a century, black holes had been objects that rewarded inference over spectacle. Now, the most convincing evidence for the one in our own galaxy would come from the long memory of the sky itself. A single star, if watched patiently enough, could become a witness. Among the most important of these stars was S2, also known in the UCLA group's notation as S0-2. It circles Sagittarius A star on an orbit of about 16 years, close enough and fast enough that its motion became a kind of natural experiment in strong gravity. Over time, the repeated tracking of stars like this allowed astronomers to infer that an invisible object of about 4 million solar masses occupies a very small central region. That combination of great mass and compactness is precisely the sort of evidence that transforms a black hole from an elegant hypothesis into the only currently known explanation that fits the observations cleanly. The Nobel Prize in Physics in 2020 captured that turning point with unusual precision. Roger Penrose received 1/2 of the prize for showing that black hole formation is a robust prediction of general relativity. The other half went jointly to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. The Nobel language itself is worth noticing. It is careful. It does not simply leap from data to rhetoric. Yet in the same official explanation, the committee states that a supermassive black hole is the only currently known explanation for the invisible. extremely heavy object controlling those stellar orbits. That is how scientific certainty often sounds at its most mature, not triumphant, but exact. There is also a human texture to this part of the story that deserves to be felt. Genzel and Gez did not see the black hole in the everyday sense. They built, over many years, a dynamical case around it. Their work depended on technique, competition, endurance, and a kind of long-range confidence that a pattern would eventually emerge if the observations were good enough and the time baseline long enough. The stars around Sagittarius, a star became moving markers, tiny bright particles in a gravitational script written by something that emitted almost nothing of its own. The resulting picture was, in some ways, more powerful than a simple image would have been. It showed the invisible object ruling its environment through motion. Exactly as Michel had once imagined, dark bodies might reveal themselves through the behavior of visible companions. The oldest intuition in the story had come home. But now it had come home with infrared detectors, adaptive optics, and decades of data behind it. And yet, even this did not exhaust the black hole's transformation into reality. There remained another threshold, one that had been anticipated since Einstein first predicted gravitational waves in 1916. If black holes existed in binaries and spiraled together, then their final merger should shake space-time itself. For a long time, this belonged to the realm of almost impossible measurement. The strain expected at Earth would be absurdly small. The instrument required to detect it would need to register changes in length far smaller than an atomic nucleus across arms kilometers long. It was the sort of challenge that made even sympathetic physicists wonder whether human technology could ever make the idea operational. But once again, black hole history moved forward through patience rather than spectacle. On September 14th, 2015, the two advanced LIGO detectors in the United States observed a transient signal that rose in frequency and amplitude exactly as general relativity predicted for the inspiral and merger of two stellar mass black holes. The event, later called GW 150914, was published in 2016. The inferred initial masses were about 36 and 29 times that of the Sun, and the final merged object about 62 solar masses, with roughly 3 solar masses converted into gravitational wave energy. It was the first direct detection of gravitational waves, and also the first direct observation of a binary black hole merger. The signal did not show a black hole by reflected light or optical outline. It did something more radical. It allowed astronomers and physicists to hear the dynamics of black holes through space-time itself. This was a new sensory mode in the history of the subject. Earlier generations had inferred black holes from companion stars, X-rays, quasar energetics, and stellar orbits in the galactic center. LIGO added another kind of evidence entirely. It detected the coalescence of invisible objects through the ripples they launched across the structure of space-time. For black hole history, that mattered at more than one level. It confirmed that binary stellar mass black hole systems are real. It confirmed that they merge. It confirmed that the violent dynamics near merger conform strikingly well to Einstein's theory. And it gave the long theoretical tradition around black holes a kind of acoustic reality. The object that once seemed too strange to inhabit thought was now ringing in the detectors. There is a quiet beauty in the sequence of these confirmations. Genzel and Gez showed that stars in our own galaxy move around an unseen, supermassive compact object. LIGO showed that smaller black holes in distant systems collide and merge in precisely the way relativity predicts. One line of evidence is slow, orbital, and almost classical in feeling. The other is sudden, transient, and dynamical to the point of violence. Together, they expanded the black hole across scale and method. The universe was not merely permitting such objects in isolated corners. It was populated by them. They sat at the heart of galaxies. They paired, inspiraled, and fused. They had become part of the ordinary inventory of cosmic reality, even if nothing about them felt ordinary at all. Then came another threshold, one that would have seemed almost like science fiction to earlier generations. In April 2019, the Event Horizon Telescope collaboration released the first image of the black hole at the center of the galaxy, M87. Strictly speaking, it was not an image of the black hole itself, because the hole remains dark. What the world saw was the bright ring of emission from hot plasma around it, with the central shadow produced by the black hole's strong gravitational effects on the paths of light. The collaboration described the image as revealing the black hole at the center of Messier 87, a giant galaxy in Virgo, with a mass of about 5 billion suns. Here, at last, was something visually iconic. The black hole had not ceased to be indirect, but the indirectness had become visible in a form almost anyone could grasp. This moment carried extraordinary symbolic force because it seemed to resolve a long tension in the history of the subject. For more than 2 centuries, black holes had been objects known through theory, through logic, through orbital influence, through X-rays, through stellar motions, through gravitational waves. The Event Horizon Telescope did not replace those methods. It crowned them with an image that condensed the whole journey into a single, humanly legible form. One does have to be careful here. The image did not eliminate all inference. It depended on a global network of radio telescopes, sophisticated interferometry, calibration, modeling, and reconstruction. It was not a casual snapshot, but for the broader imagination of science, it mattered immensely that the edge of the invisible had acquired a visible outline. And then, in May 2022, the Event Horizon Telescope released the first image of Sagittarius A star, the black hole at the center of our own Milky Way. This result was, in some ways, even more emotionally resonant than M87 star, because it connected the historic dynamical work of Genzel and Ghez with a direct imaging campaign focused on the same central object. It also posed severe technical challenges. Sagittarius. A star is much smaller on the sky than M87 star and changes more rapidly, making it harder to image cleanly. Yet the collaboration succeeded, offering the first direct view of the black hole at our own galaxy's heart. By then, the story had crossed an extraordinary distance. An 18th century speculation about dark stars had become a 20th century mathematical struggle, then an astrophysical inference, and now a 21st century image. It is tempting, at this point, to ask the question people often want from history. So who discovered black holes? The temptation is understandable, but the story itself resists that kind of compression. Michel and Laplace glimpsed the possibility of invisible, gravitating bodies. Schwarzschild uncovered the geometry that later became central. Chandrasekhar showed that some stars could not end quietly as white dwarfs. Oppenheimer and Snyder described continued collapse. Finkelstein clarified the horizon. Wheeler helped give the object linguistic and communal reality. Kerr made it astrophysically richer through rotation. Penrose showed that collapse toward black holes is robust in general relativity. Bekenstein and Hawking transformed them into thermodynamic objects. Muraden, Webster, and Bolton made stellar mass candidates persuasive. Lyndon Bell and Rees enlarged the scale to galactic nuclei. Genzel and Gayes measured the galactic center's hidden mass through stellar orbits. LIGO detected black hole mergers directly through gravitational waves. EHT revealed the visible shadow of the invisible. Black holes were discovered many times because the object itself had to become real in many different ways before science could fully live with it. That layered discovery tells us something deeper than the history of one cosmic object. It tells us how science handles realities that do not meet the senses halfway. Human beings often imagine discovery as a sudden encounter, a thing seen once and recognized forever. But some truths enter culture more slowly. They must first be tolerated as hypotheses, then stabilized in theory, then connected to natural processes, then traced through instruments, then measured in many incompatible-looking ways until resistance begins to fail. Black holes were like that. Their history is a study in the ethics of inference, in the patience required to trust what cannot be touched directly, and in the discipline needed to let evidence accumulate across generations rather than demanding a single heroic moment. And perhaps that is why black holes have remained so compelling. Even beyond physics itself, they forced scientists to keep returning to first questions. What counts as seeing? What counts as proof? What sort of reality can exist behind a horizon, beyond direct report, and still be known to us through law, measurement, and consequence? In answering those questions, scientists were not only discovering black holes, they were also discovering something about the mind's own reach, about the strange capacity of thought to move past what the eye can hold and still remain faithful to the world. The darkest objects in the cosmos became, in the end, one of the clearest demonstrations of how knowledge grows. Now the story settles into a different quiet. The black hole has entered reality so fully that it no longer needs to fight for existence in the way it once did. Yet the deeper questions it opened are still alive. Horizons still trouble our understanding of information. Singularities still point toward limits in our theories. Quantum gravity still waits beyond the threshold. The old struggle over whether these objects are real has given way to harder questions about what they are, how complete our current description of them can be, and what further transformations in physics may still be hidden behind the evidence we have already learned to trust. And now, as our journey through this story begins to quiet, what remains is not only the image of a black hole itself, but the long human effort it took to understand that such a thing could exist at all. What once appeared as an absurd consequence of mathematics gradually became one of the deepest realities modern science has ever learned to describe. In following that path, scientists did not simply add another object to the map of the universe. They changed the way we think about matter, gravity, light, time, and the limits of what the human mind can accept before evidence finally teaches it otherwise. There is something deeply humbling in that process. A black hole cannot be encountered in the ordinary way. It cannot be touched, properly seen, or understood through the habits of everyday intuition. It had to be approached indirectly, through equations, through arguments, through decades of doubt, and through the patient reading of faint signals arriving from very far away. In that sense, the discovery of black holes is also a story about the discipline of thought itself. It is a reminder that science is not only powered by brilliance, but by patience, restraint, and the willingness to remain with a mystery long enough for its shape to emerge. And perhaps that is why this story lingers in the mind. The scientists who helped uncover black holes were not only exploring distant regions of the cosmos, they were also revealing something about human curiosity, about our strange ability to imagine beyond experience, and then slowly test whether reality is even stranger than imagination. The universe still holds many such dark places before us, quiet regions that do not yet fit easily into our understanding, somewhere, perhaps even now. Another idea that seems too strange to be true is waiting for its own century of questions. And as this chapter comes to rest, that may be the most beautiful thought to carry with you, that knowledge does not end at the edge of mystery. Very often, it begins there,